Alright, this is an example of a hypothesis test, just so you can kind of get the idea of what it is we're doing when we do one of these. Alright, again, we're going to do most of this on our calculator, but it's really important that you can visualize what's going on here. Alright, we got a company that's claiming that their method of gender selection increases the likelihood of having a baby girl. Alright, these tests from the method of gender selection involve 14 couples who eventually gave birth to 13 girls and a boy. Alright, we're going to use the given claim and the preliminary results to calculate the value of the test statistic and use the format of the test statistic on the previous slide. The previous slide is where we computed it and showed how to compute it. Those formulas basically. Alright, so basically what's going on here, normally we think of the likelihood of having a girl to be 50-50. Alright, I got a baby coming. I don't know what the sex is going to be. 50-50 shot of a boy or girl. Alright, this company is saying if you take our product or do our gender selection process, whatever it is that they do, we'll increase the likelihood of you having a girl. Okay, so 14 of these couples who went through the treatment had their babies. 13 of those 14 were girls and one was a boy. Alright, so significantly higher than 50% of them were girls. Alright, now testing our claim. The claim is that what we believe, or what the company wants to test, is that their method of gender selection works. So that would mean that they believe that the proportion of people who take or who use their method would have baby girls at the rate higher than 50%. Okay, so remember, we have to have one of them equal when we do a hypothesis test. So our null hypothesis is going to be the proportion of the population of people who do this procedure that have a girl is still 50%, 0.5, right? And the alternate hypothesis, remember, that's the one that we want our claim to be, or this company would want their claim to be. They're claiming that it's greater than 50%. All right. Now, we can't ever, we can't use an inequality here. I mean, technically we could, but we need an equals because we want something to go in the center of that bell curve. Because without it, we can't determine probabilities. So that's why we need an equals here. So we're going to put this p hat in the middle, and then we're going to have we're going to look to see if we have significant evidence to prove that this is correct. Alright, now what this is saying, we work under the assumption that this is true. Even though we believe this to be the case, or that company that does the gender selection believes this to be the case, we work under the assumption this is true, so we have, again, a center of that bell curve. Alright, so this is the assumption that p is equal to 0.5. Our sample proportion, p hat, is 13 out of 14, alright, which is 0.929, roughly 93%. Alright, now here's our setup. Our test statistic. Oh, sorry, skipped one. The test statistic comes from the z value, comes from p hat, the actual number from our data. So that's the 0.929 here. P is the claim value. So that's we claim it to be 0.5. All right, that's the 50-50 shot of having a boy or a girl. All right, P, this is the same P from above. That's that same 0.5 from above. Remember, Q is 1 minus P, right? So 1 minus 0.5 is another 0.5. And then N's the sample size. Okay, so all we're doing is we're plugging into this formula that we talked about in the previous video. All right. This is a z-score. Remember, a z is a measurement, a possible value from the data set, minus the mean. The mean of the sample proportions is the population proportion. And then we divide by the standard deviation. This is the standard deviation of this thing. Okay, p and 1 minus p. So we plug it in there, we do all the math, subtract here, multiply, divide, take the square root, do all that math, we end up with around 3.21. Alright, and we've talked about before, if your z-score, and this is a z-score, right? If your z-score is bigger than 2, then that's considered unusual. Okay? Alright, now, again, a visual. This is just the test statistic. Again, our calculator is going to compute this for us, but our test statistic is how far away this sample proportion is from the claimed population proportion. Right? It is roughly 3.25 standard deviations away from this claim. So it's extremely rare to see something this far away if this is true. Right? Under the assumption that this is true. Right? Now here's a visual. Here's a bell curve. Again, we have a bell curve because the distribution of sample means is roughly bell-shaped once we get up to a certain height here. All right, what's in the middle of the bell curve? Well, the middle, like we said, is H naught, or the claimed hypothesis, the claimed value of the population proportion. So that 0.5 is in the middle. All right, what's considered rare? Well, we've been talking all semester that 5% is like our cutoff. All right, we will tweak that. We will use 1%, sometimes 10% this semester or the rest of the semester, but normally it's 5%. All right, so remember that's that shaded area right there, 5% in that upper tail. Now, we could also have talked about a 5% in the lower tail, okay? But this company is saying that they're claiming that they can increase the probability you have a girl from 0.5 to something significantly higher than that. So that's why we're using the 5% up in the right tail rather than down here. They're not decreasing the likelihood that you have a girl. They're saying that they increase it. So that's why we're shading up here in the right tail. All right, then the next thing to ask yourself, what's this critical z value? What number and what z-score basically separates the bottom 95% from the upper 5%? Right? And remember, how do we compute a critical z value? We use the inverse normal. Inverse normal, you take in area to the left, and the area to the left here is 0.95. That'll give us the critical number that goes right here where that shading starts. So 1.64 round into 3 places, 1.645. Right, now remember that's a z-score. This 0.5 represents the population proportion for the likelihood we have a girl. All right, so that's our cutoff. This 1.645 is our cutoff. If anything falls beyond that 1.645, then it's extremely rare, meaning that it only has a 5% or less chance of happening if this claim is true. All right, our sample proportion, that 0.929, that 0.93, is so far away from this claim of 0.5 that the z-score for that number in these distribution of the possible sample proportions, which is what this black line represents, the z-score for this sample proportion that we're seeing is around a 3.21. Well, here's 1.645 right here. So that means that 3.21 is way down here. Okay, this area right here is called the critical region. A lot of times people call it the rejection region. If a test statistic falls in the rejection region, then we'll reject the claim that this 0.5 is more than likely not true, because we just saw something right here, this 0.929, that is so rare that there's less than a 5% chance of it happening if this is truly the population proportion. All right, so we reject that the claim that 50-50 shot is the population proportion, and that the actual proportion is actually greater than 0.5.